everybody. So just really quickly before we get into the lecture for this module's content, I want to go over what is expected for Module 3, Week 4. So we have finished up Module 2, and so we are partway through Week 4 for Module 3. And so you should be working on completing the reading for this week, which actually Chapter 3, Geodesy and Transformation in Geospatial Concepts, the Fundamentals of Design, or Fundamentals of Geospatial Science. So in the intro video for Module 3, I made a mistake and said Chapter 3, Communication and Design, and so that was my mistake. Communication and Design is actually Chapter 2, and when I was transferring over into my new slide, I just made a little mistake there. So just wanted to make sure that was clear for everybody that we're reading Chapter 3, Geodesy and Transformation in the text for Module 3, Week 4. We should also be watching the lecture videos, so that intro to Module 3 and the guest lecture recording with Katrina Nystrom is up on Canvas on the guest lecture page. And so both those videos are there. The first one is a YouTube video, and then the second one is a link that you'll require a passcode. If you attended that, you would have received an email with that passcode. So be looking for that to access the lecture if you want to review it. And then this video, lecture, datum, I don't even know them. We should all be participating in the discussion forum, which is based around the guest lecture that was this past week. And so that'll be due on Tuesday, September 22nd by 11:59 p.m. And then this week we have a lab that has 2 parts. So it's all a part of the same lab. It's just broken up into different sections just to keep you guys on track with file management. And so there's a pre-lab working with projections part 1. And so each of these are separate assignment pages. So make sure that you're submitting the requirements for each part of the lab in their respective assignment pages. And so we have the pre-lab working with projections part 1, and then the rest of the lab, which is learning about projections using ArcGIS. Both of these are due also on September 22nd by 11:59 p.m. There will be a quiz this week, and so this will be just up to the content for this week and not for the whole module. So it will open up between Thursday, September 17th at 6 p.m. and be open until Tuesday, September 22nd at 11:59 p.m. So you have between those dates to take the quiz on your time. Again, all quizzes are open book and open note, and you have about an hour to complete the quiz, and you have 2 attempts, and the highest score will be kept out of those attempts. Okay, so let's get into this week's lecture, Geodesy, Datums, and Coordinate Systems. So we're going to be talking about measuring the Earth in a few different ways. And so we always have this question, seemingly, is the Earth flat? Well, by 450 BC, we admitted the Earth was round. Then we denied it. Then we admitted it again. And here we have come full circle, haha, get it, to questioning the shape of the Earth once again. So good thing you're in this class, because you're going to be learning about all the reasons how the Earth is not actually flat, but it is not exactly round either. And so we'll talk about all the different ways that we figured out about mapping the surface of the Earth. So we talked a little bit about geodesy before. So geodesy is a branch of applied mathematics. It is the science of measuring and representing the size and shape of the Earth, the exact position of points on Earth, and the study of Earth's gravitational and magnetic fields as they change over time. Since ancient Greece, mathematicians and philosophers have speculated about the size and the shape of the Earth. Around 250 BC, the ancient Greek philosopher Eratosthenes made a remarkably accurate estimate for his time based on this equation that's displayed in this slide. In this equation, the arc S is the distance between 2 points on a sphere, exactly north and south from each other. One divides 360 degrees by theta, an angle created by extending an imaginary line from each point to the center of the Earth. Then you would multiply that value by S. Eratosthenes observed that in the town of Syene, on the day of the summer solstice, the midday sun shone to the bottom of a well, casting no shadow. This phenomenon led him to conclude that the sun's rays were perpendicular to the surface of the well on the day of the summer solstice. He also measured the angle of the shadow created from an obelisk in Alexandria on the same day in a later year. This is what provided Eratosthenes with the angle theta. The length between Alexandria and Syene provided him with the distance S. With these measurements, he estimated that the Earth was approximately 250,000 stadia. Though there is some variation on how long each stadia was, this would be around 25,000 miles. The currently accepted value for the circumference of the Earth is 24,901 miles, so they were really close. So before we go a little bit further, we hear a lot about the ancient Greeks and how, the mathematicians were really able to figure out the exact, or really close to the exact shape of the Earth. I just want to also acknowledge that there are many cultures who understood navigation and created maps. Some of them even long before the Greeks, some of them after, but either way, all these systems were good. A lot of what the standard mapping and cartography practices are today do follow what was learned in ancient Greece, but again, I just wanted to discuss some other map makers and navigation or navigators. So here we have some examples from Polynesian and Micronesian navigators. This period of early navigation was between 1300 and 900 BC. So traditional Polynesian navigation was used for thousands of years to make long voyages across thousands of miles of the open Pacific Ocean. Navigators traveled to small inhabited islands using wayfinding techniques and knowledge passed by oral tradition from master to apprentice, often in the form of song. So tribal elder knowledge really comes into play here, which I think is really interesting. So generally, each island maintained a guild of navigators who had very high status. In times of famine or difficulty, they could trade for aid or evacuate people to neighboring lands. As of today, traditional navigation methods are still taught in the Polynesian outliers of Taumako in the Solomon Islands. Polynesian navigation used some navigational instruments which predate and are distinct from the machine metal tools used by European navigators, such as the sextant, which was first produced in 1730. The sea astrolabe from around the late 15th century, and the marine chronometer invented in 1761. However, they also relied heavily on close observation of sea sign and a large body of knowledge from oral tradition. Both wayfinding techniques and outrigger canoe construction methods have been kept as guild secrets, but in the modern revival of these skills, they are being recorded and published. Tupaia, a Polynesian navigator, assisted Captain James Cook on his first voyage of Pacific exploration. Tupaia drew a chart of the islands within a 2,000-mile radius to the north and west of his home island in Raiatea. Tupaia had knowledge of 130 islands and named 74 on his chart. Tupaia had navigated from Raiatea in short voyages to 13 islands. He had not visited Western Polynesia, as since his grandfather's time, the extent of voyaging by Raiateans had diminished to the islands of Eastern Polynesia. His grandfather and father had passed to Tupaia the knowledge as the location of the major islands of Western Polynesia and the navigation information necessary to voyage to Fiji, Samoa, and Tonga. So here is Anaximander of Miletus. He was around from around 610 to 546 BC, and he was a part of a school of philosophers who studied geometry, astronomy, geography, and more. And I just want you to take a look at how, important and smug he looks before we see his rendition of the shape of the Earth. And just to put things into perspective, we talked a little bit about, the motivation of the map makers a little bit in the last discussion. And so we'll go ahead and take a look at this next slide here. And so this is Anaximander's Earth. And so thankfully we've come a long way and taken information from a lot more accurate and actually mathematically calculated measurements of the Earth. Okay, so here we have the geoid. In the 17th century, Sir Isaac Newton developed the theory of gravity. Newton theorized that the rotation of the Earth would introduce outward centrifugal forces, which would counteract the pull of gravity. These forces would cause Earth to take the shape of an oblate ellipsoid, meaning it is a bit wider around the equator than around the poles. Before people could go about developing a system for defining the location of points on a 3D surface, first they had to define the surface itself. The need to measure elevation resulted in the development of additional models of Earth. Elevation is a relative measurement equal to the height above mean sea level. Because elevation is relative to mean sea level, changes in the mean sea level result in changes of elevation. Accurate vertical measurements such as elevation require a different model of Earth called a geoid. A geoid is a surface model of Earth based on gravity. No land masses exist on the geoid surface model, and mean sea level covers the entire planet. Places where gravity is stronger or weaker change mean sea level, creating an undulating shape. As we'll see in the next couple of slides, the actual surface of the Earth is very irregular and has mountains and valleys. Even if we didn't have those things, different densities beneath the Earth's crust cause differences in the gravitational pull at different parts of the Earth, undulating its shape. And so we have a few different ways that we measure the surface of the Earth. And so we have our topographic surface, which is the real surface of the Earth or the ground. We have the reference ellipsoid, which is a mathematical approximation. And then we have a reference geoid, which is the mean sea level surface. The irregular, non-geometrical shape of the geoid is challenging to work with directly. For mapping purposes, you need to transform the geoid into a smooth, mathematically defined surface model called the reference ellipsoid. Because the geoid and the reference ellipsoid are not an exact match, there are multiple reference ellipsoids used today, each optimized for different regions of the Earth.